Assalamualaikum everyone. Welcome to our channel, and today we are going to walk you through our discrete structures course project. And this project combines mathematics, graph theory, and real world economic data. This project is completed by me, Muhammad Ali Mahdi, and my other two teammates, Ahmed Musa and Muhammad Ahmed Yusuf.
Our project is called Item Level Core Price Movement Network using CPI data. The big question we are answering is when prices of different consumer goods move together across Pakistani cities, what does that network look like and how does it change over time? We are three group members and we built this entire pipeline in Python using data straight from the Pakistani Bureau of Statistics website. Let us dive in. Our data comes from the PBS, Pakistani Bureau of Statistics. It contains monthly retail prices for over 50 consumer items recorded in cities all across Pakistan spanning 3 full years 2023, 2024, and 2025. The items range across 7 categories: food staples and grains, meat, poultry and dairy, oils, condiments and sweeteners, fruits and vegetables, non food essentials, utilities and transport, and clothing and miscellaneous. Now here is the core idea from our discrete structures course. Instead of treating cities as nodes, we treat consumer items as nodes. Two items become connected by an edge if a large enough number of cities show similar price changing patterns for both items in the same year. This is a direct application of binary relations in graph construction. Our implementation is a single end-to-end Python script. It loads the PBS Excel data, normalizes product names across variant spellings, computes price change vectors, calculates cosine similarities per city, constructs yearly graphs using network X, computes all 5 centrality measures, aggregates them using 3 weighing schemes, runs temporal and hash diagram analysis, performs category and community detection analysis, and saves all outputs automatically. Libraries used include pandas for data processing, scikit-learn for cosine similarity, networkx for graph operations, and matplotlib for all visualizations. The entire pipeline is reproducible. Just provide the data.xlsx file and run the script. All outputs appear in the output folder.
So let me walk you through the mathematical pipeline of our discrete project. For each item and each city, we built what is called a price change vector, a sequence of 11 numbers representing month-to-month price changes from February to December. For example, if wheat price cost 1200 rupees in January and 1250 rupees in February, the first entry in that vector is plus 50. We do this for all 12 months, giving us a vector that captures the direction and magnitude of price movement across the year. Now, to measure how similar two items are within a city, we use cosine similarity. And as you can see, this is the exact formula of cosine similarity from our course. The dot product of two vectors divided by the product of their magnitude is a score close to 1 means both items moved in the same direction. And if the score is near to 0, it means the movement were unrelated. So we computed the similarity for every pair of items for every city. Then for a given year, we count how many cities gave a pair of items a cosine similarity above threshold tau, and we call that n sub y. If n sub y is greater than or equal to city count threshold k, we draw an edge between those two items in our graph for that year. In our final analysis, we used the tau equals 0.8 and k equals 3. Using this rule, we constructed a separate unidirected graph for each of the 3 years. As you can see, every node is a consumer item where we have 51 nodes for 51 different items, and every edge means at least k cities showed high price co-movement for this pair. And we built two versions of each graph. The first is the binary graph. Either an edge exists or it does not, with the edge weighted being n sub y, the number of agreeing cities. The second is the weighted graph, where the edge weight is instead the average cosine similarity of that item pair across all cities. And this lets us distinguish strong co-movers from weak ones. And looking at the 2023 network, you can see a dense central cluster, a food, dairy, and utility items, while energy products like LPG and high-speed diesels are isolated at periphery. And this tells us fuel prices moved quite differently from food prices that year. By 2024 and 2025, the network spreads out. The central cluster loosens, and many items from smaller isolated pairs or groups. This is a view signal that price co-movement became less uniform as inflation and supply shocks affected different sectors differently.
So, Assalamu alaikum. Hello, my name is Ahmed Musa. One of the most revealing part of our analysis was the temporal comparison across 3 years. Look at this chart. Total edges dropped sharply from 110 in 2023 down to just 36 in 2024 and further to 19 in 2025. At the same time, connected components rose from 15 to 23 to 34. What does this mean? More components with fewer edges means items are grouping into smaller, more isolated clusters. The price movements of Pakistani consumer goods become more fragmented year on year. Goods that used to move together in 2023 began decoupling by 2025. We also constructed hash diagram visible on screen now, which represents the temporal partial order across our three yearly graphs. In this structure, an edge from year 11 to from year T1 to year T2 is drawn if and only if every edge represent in the T1 graph is also present in the T2 graph, meaning T1's edge set is a subset of T2's. This gives us precise discrete math characterization of how the network structure evolves under set inclusion. We also tracked which items were persistently central across all 3 years. Vegetable ghee appeared in the top 5 centrality rankings every single year, making it a persistent hub in Pakistan's consumer price network. This is a consistent with how cooking oil prices are influenced by global commodity markets. On the other hand, some edges were transistent. On the other hand, some edges were present, existing only in 2023 between fuel and utility items, and disappeared once those sectors decoupled from food prices in the later years. So we also colored our network by category, and the patterns are striking. In 2023, cross strategy edges are abundant. Food items connect with utility items, clothing items connect with dairy. This suggests broad inflationary pressure hitting all sectors together. By 2025, the category clusters are much cleaner. Oils and condiments items cluster together, clothing items from their own isolated cluster. The network is starting to look more like what economic theory would predict, categories moving somewhat independently. To formally test this, we ran community detection using the greedy modularity maximization algorithm on each yearly graph. The detected communities were then checked for alignment with our predefined 7 categories. In 2023, most communities were mixed, containing items from 3 or 4 different categories, confirming the broad co-movement that year. By 2025, the dominant category within each detected community matched its predicted label much more closely, showing that category boundaries become economically meaningful as price dynamics fragmented. Importantly, no single category dominates as a bridge between all each other in any year. But the utilities and transport category, especially gas charges and electricity, consistently appears in high centrality position, reflecting how energy costs ripple through all sectors. So, through sensitivity analysis, we confirmed that our findings are robust across a range of threshold choices. The hash diagram formally captured the temporal partial order of our network structures, and community detection confirmed that category boundaries became economically meaningful as price dynamics fragmented across 2023 to 2025.
To summarize, we built a temporal item price similarity network for Pakistan using 3 years of CPI data. We applied cosine similarity, binary relations, and graph construction, all core topics from discrete structures.